Okay, today lecture class is 1 hour lecture class. Okay, for those who haven't filled out the attendance form, you have to fill out as soon as possible. Okay, I will continue my lecture, okay, from last topic. Okay, last week I have a stop here. Okay, I'm going to continue with this transient response from the RC delay model. Okay, and then there are a few slides I need to finish. Okay, I will finish it today. Okay, to recap, okay, what we have covered last week. Okay, last week is also on these RC wire models, okay, for the inverter. Okay, so okay, so you know what is wire delay model. Okay, if you revise back to your lecture notes, okay, so the wire models is based on the resistance, capacitance, and inductance, and then there are some of the RC models are introduced to you. Okay, that is based on the length of the wire. Okay, uh, and what else? Not only the length, okay, but also the um, uh, okay, and also the ideal case and non-ideal case. Okay, there is an ideal case and non-ideal case. Non-ideal case, we have to see the length of the wire. Okay, there are different RC models. Okay, so you can revise back. Okay, what has been covered last week. Okay, so now I will continue with the RC models. Okay, the RC models can use to analyze the transient response. Okay, once the RC model is determined from the CMOS inverter, it can easily be analyzed for the transient response. The transfer functions of these first order RC models driven by a step input. Okay, this is the transfer function. Okay, that illustrate this circuit. Okay, and by taking the inverse Laplace transform of Hs, the step response is given by these equations. Okay, this is the voltage. Okay, equals to VDD multiply exponentials with this minus T over tau. Okay, here tau means the RC. Okay, tau sometimes we call it as a time constant. Okay, this is time constant. Okay, here based on the RC, okay, the voltage, okay, can be determined. Vy can be determined, okay, based on at which the time constant is. Okay, VDD is the supply voltage. Okay, these equations can relate to this graph. Okay, this graph, okay, this is the time constant. Okay, start from 0 to 4 tau. Okay, tau here means the RC, the time constant. And then here, the y-axis here is the voltage level. Okay, or maybe we should call it as a step voltage. Okay, so different time constant, the voltage level will be different. Okay, the voltage level, we evaluate it at point which is on the curve here. Okay, this is the curve. Okay, now the propagation delay TPD is the time at which the output Vy reach to VDD divided by 2. Hence, VDD divided by 2 is equals to VDD e power of negative t over RC. Okay, this gives the propagation delay of TPD equals to RC natural log 2. Okay, so most of you know what is meant by propagation delay. Okay, so the propagation delay can also represent as RC multiply natural log 2. Okay, so if we want to express the propagation delay with the time constants, this will be the formula. Okay, this will be the formula. And then the relationship, we can see that the propagation delay is directly proportional with the time constant RC. Okay, so here already stated the relationship. Okay, delay increases with the increasing value of both R and C. Okay, so if we want to evaluate the wire delay, okay, if the wire have a large capacitance, then of course the propagation delay will be large. Okay, this is how we use the formulas to evaluate the wire model. Okay, now is the example. Okay, this example is to determine the RC. Okay, the resistance and capacitance of a logic gate. Okay, the resistance and capacitance we need to determine the value. Okay, and then we need to draw out. Okay, in the diagram. Okay, the diagram with the logic gates. Okay, so the examples here is given as sketch a 3-input NAND gate with transistor width chosen to achieve effective rise and fall resistance equals to that of a unit inverter. Okay, so this circuit is a NAND gate. Okay, it's a NAND gate. And you see here, let me see. Okay, I skipped one slide here. It should be this slide. Okay, okay, this slide, okay, is based on this slide. Okay, I should start with this first. Okay, so this is a NAND gate. Okay, this NAND gate, we need to determine the resistance and capacitance. Okay, here the NAND gate, the width of the PMOS and NMOS are different. Okay, the width are different, and you see the PMOS, the width is 2, and then the NMOS is 3. Okay, so after the width are determined, okay, then we can determine the capacitance and then the resistance of each PMOS and NMOS. Okay, so for this, to determine the resistance and the capacitance, okay, we can actually refer back to this slide. Okay, this is the slide RC delay models. Okay, that shows the values of the capacitance and the resistance for NMOS and PMOS. Okay, so you see this K is the width. So after we determine the width, so the width can use to multiply with the capacitance, then we can know what is the values of the capacitance. Okay, so for both of the PMOS and NMOS transistor, you see the capacitance just multiply with K. Okay, so later on the examples that I show you that with the solution, okay, is based on this slide. Okay, so all the capacitance are determined with the use of this diagram. Okay. Okay, so for this one, you see here, after determines the width, and then the capacitance and resistance we can draw out. Okay, this is the diagram that is with the capacitance. Okay, the capacitance here include gate capacitance. Okay, and also the junction capacitance. Okay, resistance are not draw here, are not draw in this diagram. Okay, but it is determines here. Okay, here already show you how to determine the resistance. Okay, okay, maybe I will discuss this. I need to discuss this on how to calculate the resistance. Okay, even though the resistance is not given, okay, the value is not given, but we can express it with the term R as R. Okay, so here you see the NMOS, the width is 3. Okay, so it is 3 times due to series connections, R divided by 3 plus R divided by 3 plus R divided by 3, then it is equivalent to R. Okay, if you see the diagram, just now the diagram that I show you, this one, okay, we refer to the NMOS. You see here R divided by K. Okay, R divided by K. So the width of the NMOS is 3. So it is R divided by 3. Okay. Okay, so this is R divided by 3. And then due to the reason that it is in series, so all is sum up together. So the equivalence total resistance equals to R. Okay. And then for this one also we need to use the same method. Okay, we refer to the PMOS and then we can use it to determine the resistance. Okay. Okay, now the capacitance, to determine the capacitance. So you see here, each of the capacitance here is multiplied with the width of the transistors. Okay, so the width of the transistor for PMOS is 2, so all the capacitance here are multiplied by 2. Okay, and then for the NMOS, okay, for NMOS, the width is 3, so all capacitance is multiplied by 3. Okay, after we state all the capacitance, we can actually simplify this diagram into this diagram. Okay, we lump some of the gate capacitance together. Okay, and also some of the capacitance at the output, we also can lump it together. Okay, how to lump it? Okay, you see here, this is the 5C, right? Okay, there is a 5C at the gate of the PMOS and NMOS. PMOS and NMOS. How to get this 5C? Okay, this 5C, you see here, the gate capacitance of the PMOS is 2C. Okay, it is 2C. And then for the NMOS, the gate capacitance is 3C. Okay, so 2C and 3C add up together will be 5C. So each of the capacitance, each of the transistor here, okay, the lump capacitance will be 5C. Okay. Okay, and then for the output capacitance, so you see this is the point, point Y is the output. Okay, so Y, the capacitance that are connected to the Y is 3C, 2C, 2C, and 2C. Okay, all these are junction capacitance. Okay, and then these junction capacitance are connected at the output. Okay, all these junction capacitance can be lumped together, okay, to become the output capacitance. Okay, so Y here is equals to 9C. Okay, so here already show you, okay, what is mean by 9C. Okay, and then other capacitance here 3C, 3C, 3C. Okay, this is 3C, 3C. Okay, suppose here got a 3C. Okay, but it didn't draw out here. Okay, and for others, here the capacitance, this capacitance at the source terminal, okay, they are not drawn here. Okay, we can ignore. Okay, we can just ignore. Okay, so this is how the RC are determined in a logic gate. Okay, based on the 3-input NAND gate, okay, this is the NAND gate from the previous examples. Okay, in the worst case of output falling transitions, output pulls down through the 3 series NMOS transistors. Okay, so now I'm talking about the operations of this NAND gate. Okay, so all of you, you know the NAND gate, what is NAND gate, and then the operations. Okay, so this one, you can relate it using the diagram. Okay, this is mean by in worst case of output falling transitions. Okay, means the output when it is zero, from high to zero. Okay, then output pulls down through the 3 series NMOS transistor. Okay, so when output is pulled down, so it means that the 3 NMOS must be on in series. Okay, must be on in series, or else it will not pull down. Okay, will not pull down or will not reduce to low. Okay, all 3 NMOS must be on in series. Okay, during the worst case of rising transitions, 2 PMOS remains off and 1 is on. Okay, this is means by the worst case. Okay, worst case when the output is rising. Okay, if the output is rising, means that at least 1 PMOS is turned on. Okay, here you see the PMOS here all are in parallel. They must have at least one PMOS is turned on. Okay, so that the Y will be pulled up or Y will increase to high. Okay, so you know the concept. I will not discuss further on that. Okay, but this is how we should understand. Okay, and if one of the PMOS is on and other is off, then another 2 NMOS will be on and the bottom is off. Okay. Okay, hence the series capacitance of upper 2 NMOS must also be discharged during the falling transition in worst case. Okay, when the output is transitions from high to low. Okay, the Y when it become low, start to become low, the capacitance will discharge. Okay, those capacitance will discharge. Okay, and then these two diagrams show you which transistor will be on. Okay, so RC equivalence when output is falling. So when output is falling, it means that all NMOS are on. Okay, so these are the NMOS. Okay, you must remember these are the NMOS transistor. Okay, these NMOS transistors are with the resistance and the capacitance. Okay, it's based on this. Okay, we take this when the output is falling. Okay, and then for this RC equivalent, RC equivalence when output is rising in worst case. Okay, output is rising in worst case where only the PMOS is on. So this is the PMOS. The resistance for PMOS. Okay, and this is the NMOS. Okay, and all the capacitance are still the same. Okay, we have to follow accordingly. Okay, so this is what is meant by the diagram here. Okay, as a summary, okay, although transistors are complicated devices with nonlinear currents, voltage, and capacitance voltage relationship, for the purpose of delay estimations in digital circuit, they can be approximated quite well as having constant capacitance and an effective resistance R when on. Okay, logic gates are test models as a RC network. The element delay models estimate the delay of the network as the sum of each capacitance times the resistance through which it must be charged or discharged. Okay, so this is the summary for the delay model. Okay, so this is the end of the topic. Okay, for the RC wire model. Okay. Is there any questions on this topic? Okay, I will go to another topic. It is also a short topic. Okay, no questions. Then I will continue with the next topic. Okay, I have uploaded the lecture notes. Okay, you can find it in the Google Classroom. Okay, the next topics will be transistor level circuit. Okay, you can download your lecture notes if you want to refer to the lecture notes. Okay. Okay. The topic here, okay, TTL circuit, okay, stands for transistor level circuit. Okay. This is one of the logic circuit. Other than the CMOS logic circuit, there is other types of logic circuit. We call it as a transistor level circuit. Okay, for this topic, I will cover the fundamental, okay, the fundamental theory, okay, and with some of the calculations, okay, formula and calculations, okay. Later you will know what is the difference, okay. Um, TTL circuit, uh, they are TTL inverter circuit, TTL NAND gate circuit. Okay, these circuit are also the logic circuit. Okay, except that the transistor use is different. Okay, it does not use NMOS and PMOS. It use other type of transistors. Okay, you learned before we have many type of transistors. Okay, BJT, BiCMOS, and others. Okay, other transistor that we can remember. Okay, but in this course, the transistor that I emphasize most is on PMOS and NMOS. Okay, for this topic, okay, it is not using the PMOS and NMOS. Okay, it use other transistor instead. Okay, so the outline for this topic is introductions to logic family. Okay, they are uh, uh, different types of logic circuit. Okay, and under logic family. Okay, so the logic family will be introduced to you. Okay, to have an overview. Okay, on uh, which one is under logic family. Okay, which types of logic circuit is under logic families. Okay, and then introductions to transistor level circuit. Okay, they are transistor level TTL. Okay, TTL stands for transistor level. Um, the gates that will be introduced to you will be inverter. Okay, inverters also there are TTL inverters circuit. Okay, that use other transistor. Okay, and also others logic gate as well, and gate, no gate, but I'm not going to cover on that because I just want to cover the fundamental theory on this TTL. Okay, and the power dissipations of TTL and propagations delay of TTL. Okay, so these topics will cover all this. Okay, as introductions to logic families. Okay, logic family is a collections of different IC. Okay, I think I should switch it to slide mode. Okay, logic family is a collections of different IC that have a similar circuit characteristics. Okay, logic gates like NAND gate, NOR gate are used in daily applications for performing logic operations. The circuit design of the basic gates of each logic family is the same. Digital logic circuits are manufactured depending on the specific circuit technology. The gates are manufactured using semiconductor devices like BJT, diodes, or FETs. Different gates are constructed using integrated circuit. Okay, this is a chart okay, that shows the logic families. Okay, the TTL circuit that will be discussed is undersaturated bipolar logic family. Okay, and then the PMOS and NMOS as well as the CMOS are under unipolar logic family. Okay, so you see here logic family can classify to bipolar and unipolar. Okay, bipolar logic families here means that the transistor used is bipolar. Okay, so the transistor we have a BJT, bipolar junction transistor. Okay, so that is under bipolar logic family. Okay, for unipolar logic family, okay, so you see here all include the PMOS, NMOS, and CMOS. Okay, so this is how we should differentiate, okay, different logic type of circuit. Okay, the most important parameters for evaluating and comparing logic family includes the logic level, power dissipations, propagations delay, noise margin, and fence out. Okay, so all these are the parameters for evaluations when we want to evaluate the logic gates. Okay, logic levels here normally we will evaluate the level at the input and output. Okay, so all these you all are familiar. Okay, so you just treat it as revisions. Okay, so they will be discussed in brief. Okay, for all these. Okay, so for power dissipations, this is one of the parameters for evaluations. Okay, it is measured in milliwatt. usually the product of a supply's voltage and the amounts of average current draw when the output is high or low. And propagation delay, it represents the transition time which elapses when the input level changes. The delay which occurs for the output to make its transition is the propagation delay. And noise margin represents the amounts of noise voltage allowed at the input which does not affect the standard output. Okay, and fans out with the numbers of gate input means the load, okay, driven by the output of another single gate. Okay, this is the driver. Okay, this is a driver that without affecting its usual performance. By load, it means the amounts of current required by the input of another gate connected to the output of the given gate. Okay, this is just the definitions for each of the parameters in evaluations. Okay, there are two major logics family, okay, TTL and CMOS. Okay, TTL is based on bipolar junction transistor. Okay, so this is the difference. TTL use BJT, CMOS use the MOSFET, okay, transistors. So later you will see the structures of the TTL circuit. Okay, the structures is different. Okay, it's different than CMOS. Okay, as well as TTL and CMOS technology, simple digital logic gates can also be made by connecting together diode, transistors, and resistors to produce resistor transistor logic gates, RTL. Okay, and diode transistor logic gates, DTL, or emitter couple logic, ECL gates. But these are less common now compared to the popular CMOS family. Okay, so there are other types of logic gates. Okay, you see here these are a few terms here that is based on what is the component used to construct the circuit. Okay, so here all the logic circuits mentioned here, okay, will not be emphasized in this topic. Okay, and these logic gates are less common. Okay, as already stated here, they are less common. Okay, and the most popular is the CMOS. Originally, TTL chip were fast but used lots of power, and CMOS chip used little power but were slow. Okay, so this is the comparisons between the TTL chips and CMOS chip. Okay, TTL logic IC use NPN and PNP type bipolar junction transistor, whilst CMOS logic IC use the complementary MOSFET or JFET, okay, type field effect transistor for both their input and output circuitry. Okay, so you see the diagram here. Okay, this diagram shows that the TTL use BJT. Okay, and then CMOS use the MOSFET. Okay, MOSFET and BJTs are two different types of transistor. Okay, and then they construct two different logic gates. Okay, so the structure is also different, and these two logic gates is under the same, not under the same, is under the logic family. Okay. Okay, classifications of TTL circuit. Okay, they are TTL inverter, TTL NAND gate, open collector gates, tri-state TTL gates. It is a logic family consisting completely of transistors. It employs bipolar transistors with multiple emitters to achieve switchings and main logic states. Okay, DC supplies voltages. Okay, there are some requirements to follow. Okay, when we select the supplies voltage for TTL circuit. Okay, the nominal values of the DC supplies for TTL devices is positive 5-volt supply and cannot tolerance of voltages far above or below 5 volt. Okay, uh, the DC supplies voltage is connected to the VCC pin. Okay, this is to VCC. Sometimes we call it as a VDD. For VDD it is used in a CMOS. Okay, CMOS logic gates. Okay, but TTL circuit. Okay, the pin is called as VCC. Okay, so this one you should remember. Okay, the supplies voltage for TTLs can only apply with 5 volt. Okay, cannot be above or below. Okay, and the logic level. Okay, logic level, we evaluate the logic level at the input. Okay, this is stated for the input high and input low. Okay, input high minimum means the minimum voltage that an input pin will recognize as a high. And for the input low maximum means the maximum voltage an input pin will recognize as a low. Okay, so this is the diagram. Diagram shows the logic level at the input and output. Okay, so all these again are critical voltages. We use them to evaluate um, the performance of the TTL. Okay, with the input logic and output logic. Okay, and you see here the input law. Okay, for this one, the maximum voltage used is 5 volt. Okay, so input output you see here is 5 volt. And with a low voltage level, okay, you can see the low voltage level for input and output are different. For input, okay, the range that consider as a logic 0 at the input is when the voltage level is from 0 to 0.8 volt. Okay, for the voltage above 0 volt to 2 volt, okay, the voltage is not acceptable, means cannot be interpreted, okay, as logic 1 or logic 0. So the voltage levels must fall between the high range or low range, only they can interpret as logic 1 or logic 0. Okay, for logic 1, if the input voltage falls between 2 volt to 5 volt, okay, then it can interpret as logic 1. Okay, for output as well, if the output voltage levels fall within 2.4 volt to 5 volt, so it is interpreted as a logic 1. Okay, so for the low voltage level, okay, that is to interpret as logic 0, the voltage range must fall between 0 to 0.4 volt. Okay, this we call as the output low. Others voltage range, they are not acceptable. Okay, so these two diagrams are quite important. With these two diagrams, we can evaluate the noise margin. Okay, the noise margins of the circuit. Okay, and also we can evaluate easily. Okay, which which voltage range that can be interpreted as logic 1 and logic 0 at the input and output. Okay, so this one is not difficult to understand. Okay, I have shown you before a similar diagram. Okay, like this under the static CMOS circuit. Okay, now it's about TTL inverter. Okay, so now I will discuss about TTL inverter and then how TTL inverters operate. Okay, with its structures. Okay, okay, since it is a inverter, the operation is the same. Okay, it's the same from what we know. Okay, it invert the input at the output. Okay, so operations, all of us we know. Okay, just the structure is different. So later I will show the structures of this TTL inverter. Okay, and then with some explanations how these inverters works with the BJT. Okay, the logic functions of an inverter or any types of gate is always the same, regardless of the type of circuit technology that is used. Figure 14.2.7 shows a standard TTL circuit for an inverter. Okay, so this figure refer to this. Okay, this is a standard TTL inverter circuit. You see this structure is a bit more complicated than a CMOS inverter. Okay, so this one TTL inverter circuit, they are 4 BJT. Okay, Q1, Q2, Q3, and Q4. All of these are BJT. Okay, and then each terminal are connected. Okay, okay, and also there are diode and resistance. Okay, I will briefly go through how this circuit works. Okay, with the flow of the current. Okay, uh, that make this circuit operate as an inverter. Okay, so I refer back to this slide. Okay, in this figure, Q1 is the input coupling transistor and D1 is the input clamp diode. Transistor Q2 is called a phase splitter, and the combination of Q3 and Q4 forms the output circuit, often referred to as totem pole arrangement. Okay, just now I show you there are 4 transistors, the BJT transistor. So each of the transistors, they has their own functions. Okay, and they are called differently. Okay, okay, they are called differently, but in fact they are of uh, they use the same type of a transistor, which is the BJT. Okay, uh, to discuss on the operations using the structures of TTL inverter circuit, we consider the input as high and low. Okay, so now I will discuss the operations of this circuit when the input is high. Okay, when the input is high, the base emitter junctions of Q1 is reverse bias, and the base collector junction is forward bias. These conditions permit circuit through R1 and the base collector junctions of Q1 into the base of Q2, thus driving Q2 into saturation. As a result, Q3 is turned on by Q2 and its collector's voltage, which is the output, is near ground potentials. We therefore have a low output for a high input. At the same time, the collectors of Q2 is at a sufficiently low voltage level to keep Q4 off. Okay, so based on the statements given here, okay, we can note that, okay, referring to this diagram again, okay, when the input is high, okay, the Q3 is on. Okay, we can actually expect Okay. When input is high, then output is low. Okay, output low means that the output is refer to the ground. Okay, is reduced, output is reduced, and it is low, is pulled down by the ground. Okay, so when it is pulled out by the ground, so Q3 is on. Okay, Q3 will be on, Q4 will be off, and this Q3 on is actually on by this Q2. Okay, so there is a current flow here. Okay, there is a current flow here. Okay, this is the base. So Q2 transistors will turn on the Q3. Okay, and then here R3, there is a current flow here. Current flow through the Q1 to Q2 and Q3. Okay, and here there is a reverse bias. Okay, there will be no current flow here. Okay, and here there is a diode. Okay, this diode will also block the current, if I'm not mistaken. Okay, but according to the structures here, there is how we should understand. Okay, so this is how we should know. Okay, the directions of the current flow, and then which transistor is turned on. Okay, this Q2 is partially on. Okay, it is partially on. With the Q2 is in saturation mode. Okay. Okay, so this can directly refer to this diagram. Okay, this is for when the input is high. Okay, you see here, this is reverse bias. This is the base to the emitter terminal, and then this is the current flow. Okay, current flow and the state of the transistor. Okay. Okay, I think I should stop here. I think I will continue this on Wednesday. Okay, we still have time. Okay, I will stop here. Okay, let me check your attendance. Should I expect 27? Now it's 30. Just now I see 31. Okay, I am not sure the 31 is including my presentations or one student. I saw just now one student left. Okay, it's 27. Okay, I received all your attendance form. Okay, except just now I see one student left. Okay, never mind. I will recheck back. Okay, I still have another attendance record that I can use to check. Okay, I think we can dismiss class now. Okay, later on still have another tutorial class. Okay, one group of students need to stay back. Okay, thank you.